During the training process, you might find that certain neurons become unresponsive or they die. What is the underlying cause for this? Neural networks are great for machine learning problems and produce results that are almost magical provided your training data set is large enough. But that doesn't mean everything is cool when you use a neural network. Neural networks are prone to several problems that you have to address and mitigate. We'll cover some of these issues, the problem of vanishing and exploding gradients and dying neurons in this lecture. Now, you know that a neural network is trained via a process called backpropagation. The basic concept of backpropagation is that you feed in input data to a neural network, you receive something, a predicted label or a regression value as its output. You'll compare this to the actual label or the actual value, and then use this difference to train the weights and biases of different layers of your neural network. And you'll perform this training backwards from the output layer back to the input layer. This process of backpropagation uses gradient descent optimization, where we use an optimizer to descend the gradient slope to find the best possible values of weights and biases. Now, backpropagation fails under two circumstances. It fails if the gradients don't change at all, if you can't find a way down the slope of your loss function. When your gradients don't change, your model is not getting better, it's not converging to a good value. Backpropagation can also fail if your gradients change too fast. That means your gradients move in all kinds of directions. They're not steadily moving downwards. Your model is not converging. If your gradients don't change at all while you're training your neural network, what you have is the vanishing gradient problem. Let's say you start off at some initial value of your loss function. For simplicity's sake, we'll assume that it's the mean square error here. Now, if your gradient doesn't move down the slope and instead kind of stays around at the same position in a straight line, the gradient has essentially become zero and it has stopped changing. This is the vanishing gradient problem. When your gradients do not change, you have no delta in order to tweak the weights and biases of the layers. The weights of the earlier layers remain unchanged, and your algorithm never converges to a good solution. Another problem with gradients in your neural network is the exploding gradient problem, where your gradient moves up and down explosively, spikily, suddenly. Here, let's say you start off at an initial value of the MSE, and then your gradient explodes upward and then kind of explodes downward and maybe back upward. In this case, the gradient changes abruptly. That's why it's called exploding. And once again, the weights of your layers never converge. The problem here is not that the weights don't change, they can just become larger and larger and reach insane levels such that they're essentially meaningless. The algorithm explicitly diverges and does not reach a good solution. Vanishing and exploding gradients are a real problem when you use neural networks, and they're especially true when you use deep neural networks which have many layers. Now, this was an important reason why deep neural networks were mostly abandoned for many years, and there wasn't much research going on into deep DNNs because of these vanishing and exploding gradients problem. However, recent research has found a number of solutions which can mitigate this. There are several different measures that you can put into play to cope with vanishing and exploding gradients. The first is the proper initialization of your weights and bias variables. You don't just initialize them randomly, you use a specific formula. Another way is via gradient clipping. Gradient clipping allows you to clamp your gradient values to a predefined maximum or minimum and thus reduces vanishing or exploding gradients. You can also use batch normalization. This basically involves normalizing or scaling your neuron output so that they're centered at zero and basically vary within a certain range. Vanishing and exploding gradients can also be mitigated by using the correct activation functions. You need a non saturating activation function so that your gradients remain even and don't suddenly disappear or suddenly explode. We'll study each of these in turn, starting with proper initialization. What Xavier and he noticed when they performed their research was that the variance of the outputs in each direction should be equal to the variance of inputs so that you get a neural network which is not prone to vanishing and exploding gradients. By initializing the neural network weights randomly instead of setting them all to the same value, they achieved smooth gradients. Now, the gradients can be initialized randomly using normal distribution with a mean at 0 and a standard deviation which is based on the number of inputs to that layer and the number of outputs for that layer. The standard deviation is calculated using a predefined formula. We won't go into the details of what that formula exactly is here. Or you can initialize the weights using uniform distribution, where the weights are distributed between the range minus r to plus r, and the value of r is once again calculated based on the number of inputs to that layer and the number of outputs emanating from that layer. Gradient clipping is applied during back propagation, and we try and limit the gradients to under a certain threshold which we define upfront. Most often used with recurrent neural networks. Recurrent neural networks tend to be very deep and they're especially prone to vanishing and exploding gradients. Batch normalization is another popular technique where we ensure that the outputs of neurons don't vary within any range. They are centered around zero. So typically, we zero center the inputs, which is the output of the affine transformation, before we pass them to the activation function. You can use standard TensorFlow libraries for these, or you can calculate the mean and the standard deviation, subtract the mean from the outputs, and divide by the standard deviation. Now, batch normalization works so well that if you use batch normalization, you can also use saturating activation functions in your neural network. Of all of these techniques to mitigate vanishing and exploding gradients, the use of non saturating activation functions is interesting and merits a more detailed discussion. Now, this is how a neural network looks. These are number of neurons arranged in layers. Let's say you're in the process of training your neural network and you're hoping for great things from it, but you find that the weights of the connections do not change even when you vary the input. So you're constantly passing in new input instances, but the weights aren't getting tweaked. They kind of remain the same, they remain unresponsive to changing input. When your neurons seem to be unresponsive, the first thing you should turn to look at is the activation function. Another way to describe unresponsive neurons is that the neurons may be dead. They don't change their output in response to changing input. We've seen that there are a variety of activation functions that we can use with our neurons, and these drive the design of our neural network. A pretty standard shape for the activation function is this S shaped curve. What you see here is the logit curve. It ranges from 0 to 1. This is also the sigmoid activation function, if you hear it referenced to as such. Now, the middle portion of your activation function, where the gradient or the slope actually changes, is called the active or the non saturating portion. This middle region is the active or the responsive region of your function. If you have inputs which have outputs along this region, when you tweak your inputs, the output will also change. But at either end, you have the saturation regions. If your activation function has entered the saturation region, even when you tweak the inputs, the output will be clamped to 0 or to 1. The outputs will not change. The activation function is active for a small portion in between and saturates at either end. So, if your neuron operates within these saturation regions during training, that neuron will become unresponsive, it will be dead. Once the input to the activation function is such that the output of the activation function is operating along these saturation regions, the neuron will become unresponsive. Even if you change the input, the output will not change. And if this continues throughout training, and if you can't force a neuron out of its saturation region, that neuron is essentially dead. Typically, in an S curve, saturation occurs at both ends, as you can see highlighted, which means that if your values are such that you enter saturation at the lower or the higher end, you're in trouble. This is where your choice of activation function becomes important. Let's say you choose a sigmoid or an S shaped activation function. It can saturate at either end. For example, the logit activation that you see on screen towards the left saturates for very large and very small values of input. The ReLU activation function, on the other hand, or the rectified linear unit, saturates for only very small negative values of the input. On the positive side, there is no saturation, the gradient remains smooth. Once you understand how the activation function results in your neurons saturating, you can basically tweak this activation function in order to mitigate this saturation problem. A tweaked version of the ReLU activation function is the LU or the ELU activation function, where on the negative end we have a very small exponential factor. Instead of clamping negative values of input to be equal to 0, we have a small exponential value for the negative values of input. So the value of this LU activation function, or the exponential linear unit, is linear for positive input values, and if your input values are negative, that has a gradient as well. It's exponential with a very small slope for negative values. The use of the LU activation function over the ReLU is a major improvement when dealing with vanishing and exploding gradients, and thus dying or unresponsive neurons. Dying and unresponsive neuron issues can be largely mitigated by using activation functions such as the LU, which is why it's the new favorite. The design of your neural network is highly sensitive to the activation functions that you use for your neural network layers. Now, this activation function is typically S shaped, or it can also be a ReLU activation function. But activation functions typically have an area which is the active region where they have a smooth gradient, and they'll also operate in saturation regions where even if the input changes, the output of the neuron does not change. If your activation function works in the saturation range, that neuron might become unresponsive or essentially be a dead neuron. For a neuron to be responsive, you always want it to operate within the active region of its activation function.